Hello and welcome to Objective 1.1. This is going to be a lesson for the Network Plus, and we're going to talk about the OSI model today. And before we begin, let me give you a quick overview of the things that we will cover today. I want to make sure that by the end of the video, you're able to identify all the 7 layers of the OSI model, explain the purpose and function of each layer, and make sure that you describe and know how to describe how data moves through the model during the encapsulation and decapsulation. And last thing, we're going to take a look at some common parts and devices associated with each layer. Now let's start with the big picture. The OSI model is a conceptual framework developed by the International Organization of Standardization in the early 1980s. Its purpose was to standardize how different networking systems communicate with one another. I want you to think about this as a universal net language that allows network engineers and vendors to describe network operations in a consistent way. Think of it like a process. This model, the OSI model, is divided into 7 layers from bottom up. There are layer 1, physical, layer 2, data link, layer 3, network, layer 4, transport, layer 5, session, layer 6, presentation, and layer 7, application. I get to hear a lot of people using mnemonics to remember the layers from top to bottom. One of them that you will see often is please do not throw sausage pizza away. And with that, let's get into the details. We're going to start talking about layer 1, which is the physical layer. And this is where the actual transmission of raw binary data or ones and zeros take place over a physical medium. This layer defines the electrical, mechanical, and procedural specifications for activating, maintaining, and deactivating the physical link between devices. For example, some of the physical layer components include the Ethernet cables like Cat5e, Cat6, Cat6a, fiber optic cables, network interfaces, or NICs, hubs, and repeaters. The physical layer is concerned with bit level transmission. It doesn't understand anything else. It deals with voltage levels, timing of voltage changes, physical data rates, maximum cable distances, and physical connectors used. When you plug an Ethernet cable into a computer, you're working at layer 1. Layer 2 is a data link layer. This layer is responsible for node-to-node data transfers and provides error detection and correction from the physical layer. Data link is the one that uses the MAC addresses or media access control addresses to make sure that we identify devices on the local network segment. Devices that operate at this layer include switches and bridges. The data link layer is further divided into sub-layers. One of them is the logical link control or LLC sublayer, which handles the flow control and error checking. And the other one is called the media access control or MAC, which is another sublayer and controls how devices on the network gain access to the medium. The unit data at this layer is called a frame. Layer 3 is the network layer. This layer is responsible for logical addressing and routing. The network layer determines how data is transferred between different networks. It uses IP addresses, both IPv4 and IPv6, to identify source and destination devices across different network segments. Primary device at this layer is the router. The network layer handles path determination, which is the process of selecting the best route for data to travel from source to destination. The unit of data at this layer is called the packet. Protocols that operate here include IP, ICMP, and routing protocols like OSPF and EIGRP. Layer 4 is the transport layer. This layer is responsible for end-to-end communication and data flow control between two hosts. It ensures complete data transfer through segmentation, flow control, and error recovery. The two primary protocols at this layer are TCP, which is a connection-oriented and provides reliable order delivery, and UDP, which is a connectionless protocol and provides faster but unreliable delivery. We'll explain a little bit more about this, but the unit of data at this layer is called a segment for TCP and datagram for UDP. Port numbers are also associated with this layer, allowing multiple applications to use network resources simultaneously. Layer 5 is a session layer. This layer is responsible for establishing, managing, and terminating sessions between applications. I want you to think about this of the session as an ongoing conversation between two devices. In this place, the session layer handles the session setup, the coordination, teardown, and it also manages dialogue control, determining whether communications are half duplex or full duplex. Some examples of the session layer protocols and concepts include NetBIOS, PPTP, and RPC or remote procedure call. For layer 6, we're gonna call it the presentation layer, and this layer is responsible for data translation, encryption, and compression. It acts as a translator between the application layer and the network. The presentation layer ensures that data sent by one application can be read by another application, even if they use different data formats. Functions at this layer include character code translation, such as ASCII to EBCDIC, data encryption and decryption for secure communication, and data compression to reduce the number of bits that need to be transmitted. Common examples of this include SSL and TLS encryption, JPEGs, GIFs image formats, and MPEG video formats. For layer 7 is going to be the application layer, and this layer is the closest to the end user. It provides the network services directly to the user applications, and it's important to note that the application layer is not the application itself, but rather the interface between the application and the network. Protocols that operate at this layer include HTTP, HTTPS for web browsing, FTP, SFTP for file transfer, and SMTP for sending email, DNS for domain name resolution, DHCP, and SSH for secure remote access. We're going to discuss the encapsulation and decapsulation. And this is basically that when data is sent from one device to another, it passes down through the layers of the OSI model on the sending side. At each layer, a header is sometimes a trailer, and it's added to the data. This process is called encapsulation. At the application layer, the data is simply referred to as data. At the transport is a header is added to the unit and becomes a segment or a datagram. At the network layer, another header is added and the unit becomes a packet. And then at the data link layer, both a header and a trailer are added and the unit becomes a frame. At the physical layer, of course, the frame is converted into bits for the transmission. Now on the receiving side, the reverse process occurs, and this is called decapsulation. As data moves up through each layer, the corresponding header or trailer is stripped off and processed onto the original packet, or the original data is delivered to the receiving application. It is very important because understanding how the data flows through the OSI model is going to be fundamental for network troubleshooting. And when you encounter a network issue, the OSI model gives you like a systematic approach to isolate the problem. Remember when I was talking about the process, and this is like the process everyone follows. You can start at the physical layer and work your way up, checking each layer until you find where the communication is breaking down. Now we're going to take a closer look at TCP and UDP since they're critical to understanding how data is transported across a network. TCP is connection oriented. I want you to think about this every time you hear it. Before any data is sent, TCP establishes a connection using what is called a three-way handshake. The sending device sends a SYN packet to the receiver, and the receiver responds with a SYN ACK. This is going to start making sense at some point. And then finally, the sender replies with an ACK, just for acknowledge. Only after its handshake is completed, the data starts to begin transferring. TCP also tracks every segment with sequence numbers, and the receiving device sends acknowledgements back to confirm the receipt. So in case a segment is lost or corrupted, TCP will retransmit it. This is important because this is what makes TCP reliable, ordered, and error checked. Protocols that rely on TCP include HTTP, HTTPS, FTP, SSH, and SMTP. Now, on the other hand, UDP takes a completely different approach and it's connectionless. So think about UDP as connectionless, meaning there is no handshake and no acknowledgement. The sender simply transmits the datagrams to the receiver without confirming whether they arrived. This means UDP has no guaranteed delivery, no ordering, and no error recovery. So why would you use it? Just because it's fast. Without the overhead of connection setup and acknowledgements, UDP delivers the data with minimum latency. This state this makes it ideal for real-time applications where speed matters more than perfection. I want you to think about some protocols and services that UDP is included in, and those are going to be DNS, DHCP, and VoIP and video streaming. Now, a good way to think about all of this is that TCP is like sending a certified letter through the mail. You get that confirmation that it was delivered, and then UDP is like shouting across a room. It is fast, but you have no guarantee that the other person heard you. As a quick summary, the OSI model has 7 layers: physical, data link, network, transport, session, presentation, and application. And each of them had their specific role into the communication process. We talked about how data is encapsulated and it moves down the layers and then decapsulated as it moves up. I want you to know that understanding the OSI model is essential for network technology in general, not only a Network Plus exam, but you're going to be using it in your IT career. The main idea here is that it's going to be like a common framework just to discuss and troubleshoot network communications. And with that, thank you for watching with with the Objective 1.1. And in the next video, in Objective 1.2, we're going to compare and contrast network appliances, applications, and functions. And make sure you visit network.it-learn.io for additional study resources. And I will see you in the next lesson. Thank you.